Hello students, now we are going to study the Macaulay's method or double integration method. Right? So how to apply this method? First we will study this, and then later on in the next session we will take the example of cantilever beam and simply supported beam. Just brief about the Macaulay's method and double integration method. We have to start with the deflection method, deflection equation. What is deflection equation? Deflection equation. You must know what is deflection equation. We have already derived deflection equation for both sagging bending moment and hogging bending moment, right? So for both we have same equation, that EI d2y by dx square equal to minus m, right? So this is the deflection equation. From where we have to start? You can see here there are double derivative of y with respect to x, right? If we integrate once we will get that slope, and if we integrate twice we will get the deflection, right? So if we integrate it we will get, and suppose m is a variable, m may be a constant, it may be a variable. So suppose m is variable, m is a function of x. We are assuming that m is a function of x. M is a function of x, right? So if we integrate once, then EI dy by dx, because this d2y by dx square will become dy by dx, and EI is constant, right? And integrating this, so this is minus mx, right? Integration of m. Is it okay? So once integrating we will get this equation plus some constant, we will get some constant also. So this will give the slope. This will give the slope, where dy by dx is the slope. Dy by dx is the slope of the beam at which is nearly equal to theta, right? So this will give the slope. So first integration will give the slope equation, right? Dividing by EI we will get the slope. If we integrate again we will get EI y dy by dx will be integrating y will be equal to minus mx will be again integrated, that is mx, plus the integration of c1 and plus some another constant. So this will give the deflection, the value of y, right? We are assuming that m is a variable here and as a function of x. So integrating twice the bending moment we will give the entire equation, we will give the deflection, right? So from here you will get the y as minus 1 by EI double integration of mx, because it is a variable and as a function of x, plus c1 by EI x plus c2 by EI, and c1 and c2 can be obtained using the boundary condition, right? So from here if we obtain, so y is the deflection, basically y is the deflection as a function of x, deflection as a function of x, as a function of x, right? So this y we have to obtain, right? And how to find out c1 and c2? Using the boundary conditions, right? So using boundary conditions we can obtain c1 and c2. So c1 and c2 can be obtained using the boundary conditions, right? So this is the Macaulay's method or double integration method, right? But what is the boundary condition? General boundary conditions we are talking about. What boundary condition can be used? So for simply supported beam, if we talk about the simply supported beam, suppose we are talking about simply supported beam, simply supported beam, because there are two unknowns, and for two unknowns we will be needing the two boundary conditions, right? So minimum two boundary conditions will be required for two unknowns to be solved, right? So what are the boundary conditions? C1 and C2. For C1 and C2, suppose there is simply supported beam and it is loaded with some load, whatever is the load, and after deformation, suppose this is the curve after deformation, right? Now you can see here that this is the deformation, this is the deflection, this is the deflection, right? At a certain point, suppose this is A, this is B, this is C. So the deflection at point C is from here to here, right? C to C dash. This is the deflection, which is YC, suppose, right? This we have to find out, right? So two unknowns are there, C1 and C2. To solve two unknowns, two boundary conditions are required. So boundary conditions can be found out using the simple spots, right? At this spot, at A, there is no deformation because this A point is as it is because hinge joint is there. So there is no deformation in Y direction. So at, suppose X is taking in this direction, we are taking at X in this direction, X in this direction, and total length of the beam is L. L is the length of the beam. So at X equal to 0, X is equal to 0, deformation or deflection is 0. And similarly, at roller joint, there is no deformation in Y direction, right? Because it is a roller joint, it is not allowing the movement of the particle inside itself, right? So this is reacting. There is a reaction developed from both the sides, right? RA and RB. And there will be no deformation in Y direction at point B also. So at X is equal to L, because we are taking L in this direction. This is the L length of the beam, and we are taking X in direction, so X will be L at point B. At X is equal to L means point B, Y is again 0, right? So these are the two boundary conditions by solving for required to be solved for C1 and C2, and we will get the total deflection, right? So this is the case of simply supported beam, right? And for cantilever beam, suppose we want cantilever beam. For cantilever beam, what are the boundary conditions? Suppose this is a cantilever beam, and after deformation, this is the curve, right? At this point, suppose we are taking X in this direction, or generally we take the X from free end. So most of the cases we take the X from the free end. So suppose we are taking X in this direction, suppose, right? In this direction, and L is the total length of the beam, L. So what are the boundary conditions? Boundary conditions for this case, right? When X will be L, point A, we will achieve point A from free end to A. At X is equal to L, X equal to L, there is no deformation in Y direction because the deformation is this. Suppose this is point C and deformation is YC from C to C dash. This is the vertical deformation in this beam at a certain point. But at this point there is no deformation in Y direction. To X is equal to L, Y is equal to 0. Also another boundary condition is at X is equal to L, again the slope is 0 because it is a fixed end. At fixed end the slope is always 0. So dy by dx will be equal to 0. So these two boundary conditions will be used for solving C1 and C2, for finding C1 and C2, and we can get the deflection of the beam, right? So this is how we will utilize this double integration method for solving the slope and deflection, right? And our aim will be to find out the maximum slope and maximum deflection. Suppose at this point, you can see here the maximum slope is at certain this point, right? At D point, due to certain type of loading, right? So this is the maximum deflection, because maximum deflection is very important because failure may take place due to this deflection, Y max. So our aim is to find out maximum deflection and maximum slope, and maximum slope will be at the supports, right? So this will be theta max. So our aim is to find out the Y max and theta max. Similarly here, you can see here, the Y max will be at the free end for this case only. For other case, there may be some different thing, but here the Y max is this, right? And also the slope is maximum at this point, B point, which is now B dash. The slope is maximum at this point, this is theta max, right? So our aim is to find out the Y max and theta max. So maximum deflection and maximum slope is important for us, and we will utilize first the double integration method or Macaulay's method to find the slope and deflection.